Swayam Prabha. Digital India. Educated India.
In the case of heat equation, what happens is that you are looking at u. Now you have again u of x, y, z, t. Okay, I am writing it in x, y, z coordinates. So this is space coordinates. If you want, write it in hyperspace also, you are welcome. You can write x1, x2, etc. up to xn comma t. Okay, and that means that you are in n dimensional space and something is happening. Okay, you can do that also. So the beauty with mathematics is that what you can do for one variable, you can do for any number of variables, and even infinite number of variables, and you can play havoc with all the math that you have. Okay, that's and it's a very powerful tool. So you see, when you look at the heat equation, what is U? See, the heat is always studied by what is the thing that really changes, the temperature. Okay. You want pardon me? Kinetic energy given by the vibrations of the particles. That's right, correct. Yeah, so that's the heat energy basically. Okay, so the heat energy, the characteristic of heat energy is, see, when something is hot, I don't feel a vibration. I only feel heat. I can only measure temperature. You see, when it comes to heat, what can you do? You cannot go down and measure the vibrations of the single atoms. It's impossible to do that. Okay, what you can do is what you feel is, you can only measure what you can feel and perceive. What you feel is heat, and that's temperature. So you can only measure temperature. So that's the real variable. In all heat experiments, the variable is temperature. So U is here the temperature at this position and at this time. Okay, and what happens is that the heat equation is very similar to the. So see, here is something very beautiful. You have an equation. The equations for different phenomena, they all look the same nearly. So heat equation is, on the left side you will get ut, okay, is equal to c squared u double x plus u double y plus u z z. This is what you get. Mind you, the difference is here there's a t, here there's a double t. Is something's wrong?
No, now it's what it got stuck in the middle.
Oh, it got stuck in the middle. Yeah, sometimes Zoom. Yeah. So you see, this part is still the Laplacian. I have put this c squared anyway here. There, the c squared was square of the velocity of the wave. What is the c squared here? I'll tell you what it is. Okay. And ut you get. What is ut? Is the rate of change of temperature. The rate at which the temperature is changing. Instantaneous rate of change of temperature. Okay. So if temperature is dropping at a point, ut will be negative. It will be a negative sign. And if temperature is rising at a point, ut will be positive. Okay. So this is the heat equation. This is the Fourier heat law. Okay. And this heat law, so where did this law come from? It has just come from thermodynamics. Second law of thermodynamics. And the idea of specific heat. So what is this c squared? So you see, c squared in this case, so let me write this as c squared. So we write it as delta u in mathematics, where delta is actually, del squared by del x squared. This is the Laplacian operator, plus del squared by del y squared plus del squared by del z squared. And delta is also written as del dot del, where del is a vector operator. It is I del by del x plus j del by del y plus k del by del z, where I cap, j cap, k cap are your usual unit vectors. Okay, so if you take dot product of this with itself, you see I dot I will become 1, only del x dot del x will survive, and that will give you this term. Okay, plus you will get del by del y squared plus del. So this is what it is, and so this is the equation. This is the so of course I have to, sorry, I should have put ut on the, I forgot to put, so let me write it like this. It's ut is equal to c squared u delta u. Okay, what is this c squared? This c squared is k by rho sigma. And what are these fellows? They are connected with heat. As you can expect, K is what is called as thermal conductivity. Okay, this rho is of course the density. Okay, of the material. And sigma is what? Specific heat. Okay. Right. So C squared is exactly given by these by these important constants: the specific heat of the material, the density of the material, and to the thermal conductivity. Okay.
So what is the inverted triangle called?
It's called del. So this is delta, and this is called del.
So is that also called, like, this is called the Laplacian operator?
Yeah. This is the Laplacian operator.
So what's the inverted one called?
Yeah. So this del is, what is it called? Very good. It's called gradient. This is called the gradient operator.
So the Hamiltonian operator is different.
Hamiltonian operator is basically it's an energy operator. It involves these kinds of things. Okay. Yeah, there are many. Okay. So you will see. So you see that therefore you see what's going to happen. You will have all kinds of operators. When they are all differential operators. When they operate on something, you're going to get a differential equation. What is that? That is the law of the system. You have to solve that differential equation to know what's happening to the system at any given instance. That's it, right? So you write Lagrangian, you write Hamiltonian, right, for systems. So you do that, right?
So actually, what's the difference between the Laplacian operator and the Hamiltonian operator is used in this drawing?
Difference in the sense that they have been the origins are different and the physical interpretations are different.
That also has those back variations.
That's right. So the Laplacian comes in. The Laplacian is so important. It comes in, okay. But the interpretations are different. It depends on what you are looking at. You are looking at probably some system you want minimum energy, right? Or you want to have principle of least action, or you have what is this? You want the path of shortest movement. For example, when light is moving. Okay, so there are many physical things. But finally, the beauty is that everywhere this Laplacian enters. So that's why it's such an important thing. And mathematically, it's something that is, so you see, this is all inspiration from physics. Mathematically, you get these Laplacians, and I forgot to, so let me complete this. There's something called Laplace equation. What is Laplace equation? It is just delta u equal to 0. Basically, it's just the right side 0. uxx plus uyy plus uzz equal to 0. It's just this. A function for which the sum of the second partial derivatives, pure second partial derivatives. Mind you, when it's second partial derivative, there can be mixed. I can have dou squared u by dou x dou y, which is del by del. So remember that, okay, I have to tell you something here. When you take u, x, y, z, t, okay, first derivatives are of course ux, uy, uz, ut. Okay, but second derivatives, there can be all kinds of things. You can have something called uxt, or you can have uyz. What does this mean? This means del by del t of ux, which is del by del t of del u by del x. So basically, this is del squared u by del t del x. Okay. So these are what are called as mixed partial derivatives. The pure second partial derivatives are uxx, uyy, uzz. These are the pure derivatives, and these are the so-called mixed. And there are many more. You can write. There are 4, choose 2. You can write many of them. And you also, if the function is bad, then in general uxt may not be the same as utx, and for that you need a second continuous differentiable condition. That is called as Clairaut's theorem. So the point is that therefore there are lots of derivatives moving around. Okay, but we are interested only in this pure second derivatives. Okay, and now you see delta u equal to 0, you know what this means? This Laplace equation is the, for example, what is called a steady state. So basically, you in this ut is equal to c squared in the heat equation. Steady state means what? Everything is steady. That means temperature doesn't change with time. If a function doesn't change with respect to a variable, then the derivative must be 0. If u doesn't change with respect to time, derivative of u with time must be 0. That means this part has to be 0. But that means right side is 0. That will give you Laplacian is 0 because c squared is not 0. C squared is a physical constant. Okay. Therefore, Laplacian 0 means what? Steady state. Right? You take you just take a hot plate, at the boundary you put some temperature and let it go. You maintain the temperature at 100 degrees on the boundary. Hot metal plate, let it go to infinity. You get steady state. Okay. I mean, you for an infinite amount of time you allow the so the point is that you try to so there is a situation when temperature will not change with respect to time. That's called the steady state. Okay, you do that, and what happens is that you get the steady state. And to find the function at that the temperature distribution at that point of time, you need to solve only delta u equal to 0 because ut will vanish. Right? So that's called the Laplacian. All right. So this kind of thing can also be used. For example, anything you take a charge and you have there's a potential. Okay. Then you can also use this to model potentials. You can use this to model heat flows, fluid flows. Okay. Diffusion processes. Everything can be modeled based on these equations. So these three equations are amazing equations: the heat, the wave, and the Laplace equation. If you go to college, you probably first have a course in calculus, then you have multivariable calculus. Then they will teach you vector calculus, they'll teach you vector integration and differentiation, and then finally they will teach you partial differential equations, ordinary differential equations and partial differential equations, and you will come to this, which are the fundamental equations of mathematical physics. Okay, so you will learn this. But I'm saying that it's no big deal. It's all very. In fact, I have a nephew of mine who he's in the US. He's now probably just like you, entering 12th standard. But they have a system where they can already earn college credits when they are in school itself. So he has already finished multivariable calculus and he's doing differential equations. So he told me that he knows everything. He came here for his Upanayinam from the US. So I met him. What are you doing? Probably they have started calculus. He said, well, I've finished multivariable calculus. Well, I said, what is this? So you see, I think it's high time in India that people who want to do it who want to take the race, people who are interested should be allowed to be able to do that. We should have a credit system. So then when you go to college, you don't have to do those courses. Something like that has to be done. I think IIT might do something like that because we are having the Swayam Prabha and NPTEL portals where a lot of lectures, we are giving a lot of lectures, they are being put there. So at some point probably such a thing will happen. Okay. So yes, I think we have overshot. There's supposed to be some kind of break or no, there was some break in between, right? Is it at 11? 11 o'clock, but there is no, I saw there was some break between 10.
Just a normal break, sir.
It's not so you don't, nobody wants to take a break. Fine, go. Okay, so we go ahead. So you see, therefore, moral of the story is, I would like to have a sip of water. So can you just get me my water bottle there? I would like to not to contribute to using a plastic bottle. So I carry this with me wherever I can. Yeah, thank you. Pardon? Wherein?
Where is Laplace equation applied
Okay. So there's a nice question. What is the importance of the Laplace equation by itself? Okay. So I'll tell you something very interesting. Very, very interesting. Importance. See, Laplace equation is what? A function which satisfies the Laplace equation is delta u is 0. Okay. So basically this means u double x plus u double y plus u z z is 0. And here you are assuming u is a function of x, y, z. Okay. No t. So there is no t here.
Because we are not concerned with UTT or UTX or any evaluation.
No. We are, so when you are looking at the Laplace equation, it's only Laplacian should be in all variables. Okay. So if you put a t, then you should also add utt. So Laplacian means you have to take the sum of the all space variables, all parameters. But when you do heat and when you do wave and all that, there is a time parameter which you don't confuse with the space parameters. Okay. So this is a function which satisfies the Laplace equation. Now such functions which satisfy the Laplace equation. So I just want to tell you why these functions are important. They are what are called as harmonic functions. And what are these harmonic functions? Don't confuse them with your harmonic sines and cosines. Don't confuse them with that. Though they are related in a kind of complex way. But what are these harmonic functions? They have this very beautiful property. Okay. See, suppose you take a point x0, y0, z0. Okay. I am telling you directly the three-dimensional version. What I am going to tell you also, if you remove the z, you get a two-dimensional version, and if you remove the x, y and z, you get a one-dimensional version also. Okay. You take any point, then what happens is that you can surrounding that point, you can find a sphere. You can find a sphere of some radius r naught. Okay. So there exists a radius r naught greater than 0, such that you see you enclose this point by a where is this? I wanted to use a different color. So you enclose this point by a smaller sphere. Okay. Like this, and this has radius, this is r, so r less than r naught. So I will use, so this inverted a symbol, I hope you know, means for every. So for all r less than r naught. So here's what I'm going to do. You see, I have this sphere of radius r. Okay, it's not solid sphere, it's only the surface of the sphere. Okay, right? It's just a shell. Okay, on the surface of the sphere there are points. What you do is you find the average value of the function over all the points on the sphere. Okay? Yeah, average value of u on the sphere. Surface of radius r greater than 0 and r is less than r naught. Okay? So, so here, see, here's the very, very interesting thing. So how do you make sense of this? Okay, so the way to, so let me explain. This is all calculus. So what is happening is so all we are usually used to is average of several values. Suppose you have, so I will just put it like this. I will put it as y1, y2, etc. yn. What is the average? The average is summation yi by summation of, by n. Okay, this is the average, right? Now let me make this slightly, so this is something very discrete. Let me make it very continuous. So I take a closed interval AB on the real line. Okay, and I take some function y equal to fx. Okay. Now what is the average value of the function on the interval? So you have to add the function value at every point. You have to sum all the function values at all the points, and that is integration. So the average value will become integral from a to b fx dx. This is adding all the values of f throughout the points, and then you divide by the length of the interval, which is 1 by b minus. This is the average value of the function. Right? Now, one more level of sophistication. Suppose I have a region in the plane. This is A. This is a region in the plane, and here I have a function u of x comma y. It is defined on this entire region. Okay, it's a two-dimensional region. Okay, what is the average value? It will be double integral over the A u x y dx dy. Okay, dx dy is the same as dA, volume area element. Okay, and this is summing. Remember, integration is just summing the function values. So you are taking the function values throughout that region. You are just summing up. That is double integral. It's double integral because it's two-dimensional. Okay. Then what is the average? You divide by the area. So 1 by A. Sorry, let me put area of A. This is the two-dimensional case. All right. Now you know how to do this. If it is a three-dimensional integral, if there is then you take the volume integral and do 1 by volume. So now you know what is the average value of u. It will be, okay, u of, see, this sphere is given by what? So I will just write, so integrate over the sphere u of x comma y comma z dA. So I will use the word d. I will use this. I will use ds so that you understand that. But this ds is small element of area on the surface of the sphere. Okay, and then I write 1 by 4 pi r square. This is the average value.
Yes, sir.
This is the average value. Understand? This is the average value. And so I think I'll have to take in this case. In fact, I think okay. So I am in three-dimensional case. In fact, I should not take the surface area. I should actually take this. So let me take the solid. Let me take the solid sphere. Okay. U on the solid sphere. Yeah. So let me take the solid sphere. So in this case, it will become this. So I'll have to just write this carefully. What will I get? I'll put this. Then I'll have to put this will become dV, and I'll have to put 1 by 4 by 3. 1 by 4 by 3 pi r cube. So this is a solid. Average value. Okay. So here is the interesting thing. The function is harmonic. Then this value is exactly the function value at the center.
Sir, I don't get why there are three integrals.
Because this is a volume integral. So this, when you put this, when you integrate a function of when you integrate a function of one variable, you put only this, only one integral sign you put. And the element of integration is element of one-dimensional element, which is length. So it's dx. When you do it in 2 dimensions, the region of integration is now two-dimensional area, and the element of integration is now an area element, dx times dy. You would have studied in polar coordinates is r dr d theta. I don't know whether you have studied that. No, area under a curve polar coordinates is half r square theta. Half r square theta comes from integrating r dr. Probably you have not done that. Yeah, it's like, I don't know. I wonder. It used to be in JEE syllabus, but I don't know whether it's there now. Probably not. It's not there. It's going to come. Many of this is going to come now. Some of it is going to come now. So you will be happy to see it. Okay. But anyway, it's a matter of year. 1 year plus 2. The next year you go to college. All this will be dumped into your head. Okay. So basically you can't do anything without all this. So, first things you will learn is linear algebra, okay, how to meddle with matrices, determinants, solve equations. Then they will teach you calculus, one variable, multivariable. They will teach you vector calculus. Then they will do differential equations. This is the minimum toolbox you need to do science, okay. Then of course there are other things. There's algebra. There's of course geometry, trigonometry, so many other things. Okay. So now you see. So let me get back. Since there is this amazing thing that's happening. If you take a function which is satisfies the Laplace's equation, it has this thing. This thing is given a name. It's called mean value property. That is, you take a point in the region, then there you can surround this point by a sphere. So that for all smaller spheres, if you take the average value of the function, that is the value at the center. Okay? So all the, so to repeat it, if a function is a solution of a Laplacian equation, satisfies a Laplacian, that means it is harmonic. And if it's harmonic, then it has this what is called as mean value property. The value of the function at the center at any point is actually equal to the value of the average of the function in any spherical region around that point. Okay, and this will happen up to some radius. Okay, it will happen up to some positive radius. It will happen. Okay, yeah.
Yes, sir. I don't get what are the bounds of the triple integration, the triple integrals you have shown.
So it is just a symbol. So when you are integrating a function of two variables, you use this symbol. You put a double integral, and when you integrate a function of three variables, you use this triple integral. You say, but the region is the reason for this is that the region is two-dimensional or three-dimensional. But why you actually put these integrals is because of something else. It's called Fubini's theorem, which says that if you want to integrate over a two-dimensional region, you can do this somehow by doing it in one dimension at a time. So you have to do two integrations.
Okay, one for x, one
for x and one for y. Okay, but it's not exactly that. You have to be a little bit careful. You have to choose the coordinates carefully. Okay. Similarly, when you are doing a three-dimensional integral, you put a triple integral. That is just to tell you that you are essentially having to do it in three directions, in three dimensions.
Yes.
But how you do this, so that is what they will teach you in vector calculus and integral calculus, multivariable calculus. They'll teach you how to do this. So why we write like this is that you do one integral at a time for one variable. This is what is called as iterated integration. So if you want to integrate in two dimensions, you first integrate with respect to x and then you integrate with respect to y. If you want to integrate in three dimensions, you first integrate with respect to x, then with respect to y, then with respect to z. Then of course the order matters. Then there are theorems called the Fubini theorems, which will tell you that the order will not matter if everything is nice. Okay. So this has to be done. It's like a partial integration. It is like a partial integration.
So what's the difference then between partial integration and this double integration? So now my question is more so if this is like partial integration, then what's the difference between partial integration and doing double integration or triple integration?
No. So that's what, to answer this kind of question, one has to really go through the course. See, there is a point beyond which I cannot explain because the nitty-gritty of what you have to do will have to come in. So I have to really write down, so the idea is that when you write this double integral is defined in a, in a Riemann integral kind of fashion. See, always what happens in mathematics is that in mathematics there's always this, and this is always there in every theory. I mean, all theory is finally mathematics. Take it or leave it. Okay, you have to take it. You can't leave it. Okay. See, all theory is finally math, and in math there are two things. One thing is you need to have a, what do you say? A definition for something. See, in math, definitions are gods. See, how the way math is built is that you have some foundational axioms. From these axioms you build everything. From the axioms using the axioms you make definitions. Then using the definitions you have lemmas, propositions, theorems, formulas, and you build the theory. And these axioms, these fundamental things are very, very deep. Some of them are indispensable. Mathematicians are really crazy about these things. I'll give you two examples. My famous examples. I mean, they are not my famous examples. I say them, but they are famous. Okay. So the point is, one example is if you do Euclidean geometry, That is the parallel postulate. What is a parallel postulate? It's a very silly statement. You take on a plane, you take a point and you take a line not passing through the point. There is only one line through that point and parallel to this line. If I ask you to prove it by, analytic geometry, you'll do it in no time. You will say, take the parallel line as ax plus by equal to c, ax plus by plus c equal to 0 if you want. Then a line parallel to that will be ax plus by plus c dash equal to 0. In that xy, you substitute this point x naught comma y naught. You get the c dash value, put it back, you get only one line. Okay. Now, here is a surprise. This proof is wrong. Because this proof has already used you already used the parallel postulate. Parallel postulate cannot be proved. It's so crazy that you remove the parallel postulate from the other postulates. Then from the remaining postulates, you can neither prove it nor disprove it. So enters the frightful theory of incompleteness, which Gödel started. This is the Gödel incompleteness. Okay. There is always, in any mathematical system, there is always a question for which you can neither say the answer is yes or no. No. Okay. So it's like, it's a really crazy kind of thing. So you see this parallel postulate, if you don't assume it, then God save you. Okay. One should not end up like Gödel in a mental hospital. Right. I think that's, if the history is correct, I think, yeah. So, no, but of course it's probably for other reasons. I'm saying that if you're going to say that I'm going to live without the parallel postulate, God help you. Okay, that's one thing. I'll give you another example. There's something called axiom of choice. This axiom of choice is a very, it's a basic axiom in set theory. What it says is a very, very simple thing. Suppose you have lots of sets, non-empty sets, a collection of non-empty sets. It says that you can form a new set by taking one object from each one in this collection. Okay, this is like, nobody will say that this is obvious. If you give me countless number of bags with something in them, I can take one from each bag and make a new bag out of that. What's the big deal? Of course, I may take infinite time, forget it. Okay, but the point is, will you believe that this is an axiom? If you remove it from the remaining axioms, you can neither disprove it nor prove it. So here is another baffling incompleteness. So at the very base of mathematics and logic, there are these very baffling things. You better believe them, otherwise you're done for. Okay. So moral of the story is, mathematics is crazy about defining things properly. If you don't define things properly, you will be in trouble. You know the story of the Bertrand Russell's paradox, right? Barber's paradox. There's something called Barber's paradox. You just go and, it's called Russell's paradox. Yeah. So you just go and read it up on the web. Okay. So that tells you why definitions are important. So we mathematicians, we are crazy about definitions. We want to give pakka definitions. Definition must be really a definition. A definition should not say something that's vague. A definition has to define. Define means what? It should be accurate, pakka. It cannot be vague, right? So you should be able to, so what happened to Zoom? Is there some problem? Oops. Or is there some timing thing that is, or should I reshare it? What happened to my Zoom? So maybe I will again, no, have I to rejoin? No, it's, it shows, it shows me still on the call, but it shows participant 0 and it's, my internet went away. There was a drop in internet, I think. Let's see, now, okay. I think I have to share things again. Share, screen, start. So where is this here? I am sharing. It's back. Yes. Yeah. So what was I saying? I have lost track of what I was saying. So I'm saying, Russell. So there is this Russell's paradox. Go and read it. So it tells you that if your definition, your wording should be correct. If your wording is wrong, then your definition can make you go in circles. So mathematics are always worried about a good definition. Okay. So that means you must have strong axioms. Based on that, you have to make a definition. Why you need strong axioms is your definition should not be some loosely worded thing that will give rise to some inconsistency or ambiguity or incompleteness like Russell's paradox. Okay. So you have to make a pakka definition. So you have to lay down, that's the theory. You lay down the foundations or axioms first. Based on those axioms, you make correct statements, not ambiguous statements. For that, you have to use logical operators. Then you have to formulate definitions. You understand? So mathematics is always worried about definitions. That is one part of the story. The other part of the story is you make a definition that something has to be like this. And this is like, if this is king, then he should know 64, ragas, and he should know 100 ways of fighting and all that. You make a definition like this. The question is there a fellow like that? So in math, there are two things. One thing is you make a definition. The other thing is, okay, Baba, your definition is all great. Is there one character which satisfies that definition? Can you prove that there is such a thing? So this is what is called as existence. So mathematics already has two issues. One is you should have a pakka definition for a certain type of object. Obviously, it should be something, some mathematical object with some nice properties. Okay. The next thing is, okay, great. Now, is there really such a thing? Can you show that there at least one example of such a thing? That means I have to construct such a thing. I have to show existence of such a thing. Okay. So what mathematicians do is, on the one hand, there is one group of mathematicians which strives to give pakka definitions. There's another group of mathematicians, or probably there are people who are good at both. They really construct. They show existence. See, for example, in physics, what happens is gravity waves were theoretically there before they were long shown to exist. Positron was already there before it was detected, right? So it's like that. So in mathematics itself, you can have a theory. You can, you can say that this is the definition. This is a solid foothold. This is a solid foothold based on which you have this definition. Then you have to also construct and show that there is something like that. Okay. So definition and existence are two aspects in mathematics. So what happens is that why I started this double integral, triple integral, they are all defined by a definition. Okay, the problem is that with that definition you cannot do anything. See, the problem in mathematics is definition is a very theoretical thing. It is made in such a way that you cannot tamper with it. And whatever it defines is something that's pakka. It will not create any ambiguity. Which is what it should be if you really want to call it what define means what. It should be pakka. If something is vague, it's not a definition. It's a ghost, right? It's something that's swaying and may just it may just disappear. That's not definition. All right. So you have to do that. Then there is this other thing that you have to really show that such a thing exists. So mathematics are always worried with definitions. So the integrals are always defined by definitions. For example, one variable integral, when you learn, it's called Riemann integral. It is defined as the limit of Riemann sums, and the limits being taken in a doubly infinite manner in any arbitrary way. So here is the definition. See, so how do you define integral a to b fx dx? Basically, what you do is you take this a to b, you partition it, and you partition it into pieces delta xi, and in delta xi you choose a point xi. You take the function value at xi, multiply it with the delta xi, and then you do the summation over I. Right? Now here is the important thing. Here is very, very important thing. What can change? This is I can change these. So in fact this is wait. So let me tell the following thing. Let me put this is sub n. Okay, I will so that I can explain to you what is really going on. Xin f of xi in. Okay, and this is going to give me an Sn. Okay. What you do is you let n to tend to infinity with two conditions. The maximum delta xin should go to 0 for every n. That is, these intervals should become smaller and smaller and smaller. I mean, what do you mean by n tending to infinity? You are chopping, but you can chop non-uniformly. I can keep one interval fat and kill all the other intervals and still go to infinity. That's not allowed. Every fellow has to shrink. Every partition, every piece of the partition has to go to 0. That is this condition. Then there's one more condition. The choice of xi's in this interval. You can choose any xi. For example, if you choose the left ones, you get what is called as lower sum. If you choose the right ones, you get upper sum. The left sum, right sum, lower sum, upper sum. Probably lower sum, upper sum is for minimum and maximum. Left sum, right sum is for left end point, right end point. So, moral of the story is, you see, this, you have to make a choice of partitions. So, you have to make a choice of sequence of partitions. I can do that in infinitely many ways. Okay. Only condition I have to make sure is that every piece goes to 0. Then once I have made this one out of these infinite choice of partitions, in each partition, in each subinterval, I have to choose this xi. That also I can do in infinite number of ways. Okay. What is the definition of the Riemann integral? You do this in any damn way you want. There is a doubly infinite way of doing this. Do all this and take the limit. All the limits of all these things should give you only one number. It should happen. If that happens, that is called the integral. Look at the power of the definition. You choose any sequence of partitions, only make sure that the sizes of all the pieces are going to 0, and in each subinterval choose any point, and you take this sum and take the limit as n tends to infinity. All these doubly infinitely many ways of limits. See, first of all, when you take an infinite sum, limit itself need not exist. Why should the limit of something exist? It may go to infinity, or it may just oscillate. Limit need not exist. You are saying the limit has to exist, and there is a doubly infinite way of taking these limits. So in principle, you can get doubly infinite collection of limits. Okay, but they should all be one and only one number. That number, if it exists, that is what is called the Riemann integral. You understand? And then what is the big theorem? If f is continuous, this happens. Finished. That's a theorem. Okay. Now, do you do integration like this? No, you never do that. Integrate a to b f of x dx. What you do? If I give you sin x, you will write it as d minus d by dx of cos x, and then you will use your integration as reverse of differentiation. You will sin upper limit, lower limit. You do all that and you escape. That's because you are using what is called as Newton-Leibniz formula. This is part of what is called as fundamental theorem of calculus. Integration and differentiation are inverses. Okay. But the point is, where did that come from? It came from here. You have to prove it. You don't see the proofs in school.
When do we learn the proofs?
In college. Essentially, you should learn it in college. Okay. And if they are, sometimes people don't teach it in college, then you have to learn it on your own. Okay. So the moral of the story is that, you see, when you define an integral, this is area under the curve. It's approximated area under the curve, right? See, basically what is happening is that this is the graph of the curve. Okay. The delta xin is this portion, the function value here is this much. So basically you are only taking this area. So this is this value, this is your f of xi in. Okay. And basically this total area, length into breadth. The height is, if you want f xi in, the breadth is this length of the subinterval. That's the area. You are only adding areas and you are taking a limit. Basically you are saying area under the curve exists, right? That's what you are saying. Now, you can imagine this is one variable integral. If you do two variable integral, the graph will be now a surface, and this will give you the volume of the surface above the xy plane.
Yes.
So this is volume. If you write it like this, it is the volume. Okay. The volume under the for a two-dimensional, for a two-variable function, the graph is a surface, and you are getting the volume below the surface above the xy plane. Okay, and of course 3-dimensional you can, the graph of 3-dimensional function will be in 4 dimensions because I have to plot x, y, z and then u. So this is something you cannot see. Okay.
For double integral then, would it be quad? For a double integral then, would it be quadruply infinite?
Yeah, in fact not quadruply infinite, it will be infinitely infinite. Because in the truth is in one variable, okay, you have only one way to go. But in 2 variables, so see, the one nice thing you will learn about multivariable calculus is the moment you go to more than one variable, life is very difficult. I mean, every definition will involve a infinitely infinite collection of limits. When you say some limit exists in 2 variables or more, that's a tremendously powerful condition. It will not happen so easily. It's a tremendously powerful condition. Okay. So what I want to say, the moral of the story is when you define these integrals, they are defined mathematically like this precisely. Okay. But to show that they exist, you have to prove theorems. And usually, what is the easy takeaway? The easy takeaway is whenever things are continuous, all this exists. You have to prove it. Okay. That's a different story. All right. So, but as I told you, this is a definition. Just like in the one-dimensional integral case, definition will not, you don't use a definition to integrate something. You use the fundamental theorem of calculus, Newton-Leibniz formula. So the same thing, when you do 2 variables, how will you evaluate a 2-variable integral, double integral? You can't use a definition. So what you do is, you try to evaluate it as 2 partial integrations. And breaking that you can, in most cases, nice cases, a double integral can be broken into 2 successive partial integrals. That is what is called the Fubini theorem. You can use it. And that is the reason that you use this double integral symbol there. The double integral symbol has 2 meanings. As a definition, it is a limit definition, which is very complicated. I mean, it's not useful to compute. On the other hand, when you compute it, you have to compute it as 2 integrals done one after the other. It's called iterated integration, and this is done by what is called as Fubini's theorem. Okay. Similarly, triple integral will be 3 integrals done in some order. Okay. Yes.
Sir, I have another question.
You're welcome. Yes.
Sir, why couldn't we just define the integral as an antiderivative? Why did we have to define it using the Riemann zone?
Because you see, the idea was somehow that if you look at historically, there were 2 kinds of things. They are disparate. They are not. It's not clear that they are inverse of each other. See, what happens is that on the one hand, you want to sum a physical quantity over a region of space. That's exactly your integration.
Yes.
On the other hand, you need to know the rate of change of a physical quantity in a certain direction. That's your differentiation. That these 2 are they are related is there is no hint that they are even related. People, it's Newton and Leibniz, okay, and Lagrange, all these big people. They were the people, who they discovered all this. So it's not obvious. It's not obvious. See, for example, 3-dimension. See, for 1-dimensional integral, you have antiderivative and all that. But in 2 or 3 dimensions, what do you mean by antiderivative? Because it's not a single derivative.
Okay, so it doesn't generalize very.
It doesn't generalize very easily. Okay. So then, if in 2 variables, if you want to do differentiation, there's one way to do it. You put the 2 variables together as one variable. You take x and y, write it as x plus iy, and write it as z equal to x plus iy, and make it a complex variable. And then in that one complex variable, you can have differentiation and integration, and you can still do antiderivatives. This is what is called as complex analysis. Okay. You put them together. That's complex analysis. Okay. And then the generalizations are like manifold. So this antiderivative derivative business is only for good old one variable functions. Okay. But the take away from all this is never mind any number of dimensions. You integrate one at a time. That you know to do from 11th standard. That's it. End of story. There are rules to do it. follow the rules. So you can learn. You can handle any number of dimensions. That's what higher mathematics does. It allows you to work with n-dimensional space, functions in n dimensions, their derivatives, their integrals, etc. Everything can be done. All you have to do is one derivative, one variable at a time. It's doable. So that's the theory. Okay. So So
Sir, in the beginning when we were talking about the Laplace equation, about the circle, in the sphere example you gave us, you said that if the R, it holds good for any R less than R naught. Yeah. Well, what is that R naught such that when this
so again this is no. So this is again. So I will tell you. This is again in theory. This R naught can be. You can choose any R within the domain, so that the whole sphere is contained in that domain. You can choose large enough. You can choose as large an R, but of course finite R you have to choose, because otherwise the integral will become infinite. Okay. Unless this function dies to 0 at infinity or something like that. Okay. So the moral of the story is that it's not the R that is important. So, but if you want what that R naught is, you take the domain, you give from that point, you find the largest sphere that you can put inside that domain. That will work.
So this is all radii that works with this.
So in principle, it will work for all radii. One has to be careful. I think I will. Maybe you need more conditions. A safe condition is that locally it will work. For sufficiently small R naughts at every point, if you change the point, this R naught will change. At x naught, y naught, z naught, you will get an R naught. If you go to a nearby point, this R naught will change to something else. But at every point, around that point, you get this mean value property locally. Okay. Now I'll tell you something very interesting. There are two more things I want to say before I leave. See, this is for 2 dimensions. I mean, this is for 3 dimensions. What happens with 2 dimensions? What you're saying is a function, it's on the plane in a domain. You give me any point, you have to take, there is a sufficiently small disk, solid disk, a circle with the interior. Circle is just the boundary. You take circle with the interior, there's sufficiently small disk there. In that disk, what you do is you take, but you have to only look at the, I think, just hold on. That's right. So you sum the function over the whole disk and take the average value or divide by the area of the circle. That will be the area, that will be equal to the function value at the center.
Okay. Why is that true? Like what about harmonics makes this true?
This is a big, there are things that one has to, I mean, so this is the whole theory of harmonic functions. One has to do this.
So does it work for ellipsoids also?
So I think I'm a little bit worried. No, I have to. So I think I have messed up with the number of variables. Most likely, if it is 2 variable function, then I need only the boundary, which is a circle. So so there is a correction I have to make. So let me say that, because so that you don't. So it's important in the region you take, you should take only the average value on the boundary. So this is very, very important. What I originally wrote was right. So yeah, see this number of, I should have started with. I should take the surface, and if you take surface here, I should have put only double integral, and I should have put only 1/4 pi r squared. So please correct this. This is very important. Okay, you take only the average value on the boundary. See, the idea is average value on the boundary of the region must be the value at the center. That is the condition. Not on the whole thing. If I want to take the triple integral, I have to go to 4 variable function. Okay, so it's very important. So here again, I should have. So if you take, so let me repeat it so that it's very, very clear. If you take one variable function, the fact that it is harmonic means that the value of the function at one point must be the average value at the endpoints of a symmetric interval for all symmetric intervals, sufficiently small. Okay, because it's one variable function, it's defined on an interval, the boundary is only 2 endpoints,
Yes.
right? So you should take only the average there. If it's a 2 variable function, it will be, you have to take a disk, the boundary is a circle, and you should take average value on the circle. That should be the value at the center. If it's a 3 variable function, you have to take the region will be a sphere and the boundary will only be the surface of the sphere, and you have to take the average value on the surface. The average value on the boundary is the value in the center. That is the mean value property. The average value on the boundary should be the value at the center. Okay, so this boundary is very, very important. Okay, so please correct this. Okay.
So what would be an example of a harmonic
Okay, good question. So all your force fields which give electrostatic.
Yes.
Yeah. So you see, all this you will learn when you do multivariable calculus. When you do, I don't know, people who are joining my in my project, I would like them to really derive the 3-dimensional, heat equation using the Gauss law and the Fourier heat law. Okay, and see how to solve it. I'll tell you. It's very, very easy. Okay.
Yes.
So Gauss law has to be used. You have to use what it is called in mathematics. It's called the Gauss divergence theorem. Okay, it's called the Gauss divergence theorem. You have to use that along with the heat law. Okay, and you'll get it. All right. So let me say 2 things before. My time is getting over. I just want, just for the sake of completion, I wanted to say that. So here is something. See, mathematics has its own magical things. Start with the function which is solution of Laplace equation, delta u equal to 0. I told you it's a harmonic function. It satisfies the mean value property, right? What is the mean value property? The average value on the boundary is equal to the value at the center. That's the easiest way to remember it, right?
Yeah.
For sufficiently small symmetric domains are only a point, and this should happen at every point, okay? But take functions which have this property. Take a function which has the mean value property. That means what you have to do, basically you have to find average value on the boundary of the function at every point and check whether it is agreeing with the value at the center. But finding average value requires what? It requires integration. Integration requires what property of the function? Simplest property? Continuity. So here is the amazing thing. Start with just a continuous function. Okay, it's continuous, mind you. You don't know it's differentiable. You don't know it's differentiable once. If it is differentiable once, you don't know whether that derivative is again continuous. And then you don't know whether that derivative is again differentiable. And then the second derivative exists. The second derivative may not be continuous. All kinds of things can happen. I am only assuming basic continuity because basic continuity is good enough for integration, right? For summation. Here is the amazing theorem. Amazing theorem is you start with a continuous function which satisfies mean value property, it is harmonic. That's one baffling theorem. That means that up to second order its derivatives exist and are continuous.
You repeat that again.
You start with a continuous function which has the mean value property, harmonic function. Not harmonic function. You start with a function u which is continuous, which has the mean value property at every point. Then the function satisfies Laplace's equation. That means to satisfy the Laplace equation, it means that second partial derivative, sum of second partial derivatives is 0, right? uxx plus uyy plus uzz must be 0. But to be able to write that uxx, uyy, uzz should exist. That means this second continuous, you see, second order derivatives must exist. But you started with only a continuous function. Why should it even be differentiable? So you see, this mean value property is so powerful that it makes even a continuous function second differentiable. I'll go one more step and say, not only that, it makes it infinitely differentiable. Okay, so there's absolute magic going on here. You take any harmonic function, it will be infinitely differentiable. Not only that, something more, it is what is called as analytic. Okay, it's one step more than infinitely differentiable. So that means what you're saying is you take a continuous function, just continuous function with mean value property, it is not only once differentiable, it is infinitely differentiable, it is also analytic. Now, what is the difference between infinite differentiability and analyticity? I will explain in one variable. See, if a function is infinitely differentiable, you can write what is called as Taylor series.
Yes, sir. Yeah. Yes.
Summation n equal to 0 to infinity, coefficient, Taylor coefficient is nth derivative at x naught divided by factorial n into x minus x naught to the power of n.
Yes,
This is called the Taylor expansion. A function, the beautiful thing is, there are functions which may not be differentiable, that means you cannot write the Taylor series fully, but it may, if it differential up to n times, you can write what is called as nth Taylor polynomial.
Yes, sir. Yes.
Alright?
Yeah.
Now, if it is infinitely differentiable, you can write the Taylor series.
Yeah.
What happens is, here is this amazing thing. This Taylor series it's a series, right?
Yeah.
It need not even converge.
Yeah.
It may fail to converge.
Yes. Yeah.
Then that is the worst case. The next case, it will converge but to some other function, not to the original function. You start with the function is infinitely differentiable, write the Taylor series, you will get some other function. That can also happen. What is the best possibility? We start with the function, write the Taylor series, it converges back to this function. This is what happens with all the usual things, sine, cos, exponential, log, all the usual things that you do. This is what is called as analytic. Analytic function is situation. They are in the situation that you write the Taylor series, the limit of the series is your function, it really converges. Okay? And all your textbook functions, sine, cos, trigonometric, inverse trigonometric, logarithmic, exponential, hyperbolic, inverse hyperbolic, blah, 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 all those things are all nice. You don't even see this. Okay? Now, what I am saying is, take a continuous function, which has a mean value property. Then it is analytic and harmonic. Okay? So, what is the amazing thing? You take a harmonic function, which is what? Second continuously differentiable function, which is the solution of the Laplacian. What happens? From second continuously differentiable, you get infinitely differentiable and analytic. Okay? So you get something absolutely amazing. So that is the power of harmonic functions. And finally, physically, what you are saying is, how does a function behave? Physically, it's just mean value property. At every point, the function value is exactly the average value on the boundary for a symmetric domain. Such functions are analytic. They are infinitely differentiable. That is the whole theory. Okay. So these harmonic functions they are very, very important. Okay. But physically, it's very, very easy to see. You want to recognize an harmonic function, take a point, then try to find average values of the function around. If beyond from a certain stage onwards, you are getting all average values gives you value at the center, then you have a harmonic function. Okay. You can even numerically, verify it. Okay. So what does it mean? If the average value is the value at the center, it means at some points in the boundary, if it takes greater values, to compensate for it, at other points it will take lesser values. So the average, it cannot just blow up, So the total value on the boundary is controlled by the value inside. That's what happens. You see, you will see a parallel of this when you study complex analysis, that the value of the analytic function on the boundary is controlled by the values inside. This is what is called as the Cauchy integral formula. Okay, so you will see such things. So moral of the story is that this is a deep. These analytic functions are very deep. So that's one thing. Then the other thing is, I wanted to give you a proof of. I thought that I will give proof of at least one. At least wave equation. I thought I will prove. Okay. How much more time do I have? I should stop. Okay. So now. Okay. So I have this habit of I can just go on and on forever. So I think I'll have to find some other day where there is an empty slot and again bombard you. All right. So anyway, so what I am as far as my projects are concerned, I would like people to understand heat equation, wave equation, solve them. Of course, you are going to see this when you go to college in 1 or 2 years. Okay, but then it's good to see. I'm saying it's no big deal. You can still learn it. Okay. That's one kind of thing. Then the other thing is, you can also do some, what does it geometrically mean to solve a differential equation? Okay. So in general, ordinary differential equations, you are trying to fit graphs of curves to direction fields. And in partial differential equations, you are trying to find surfaces,
Yes.
okay, for which the normal directions are given. Okay, so to understand that geometry and methods of solving those things, so that's also something that you can do. Okay, and of course there's also meaning. For example, second order ordinary differential equation means that you're also bringing in the curvature of the curve. The second derivative has got to do with the curvature. Okay, so that's where differential geometry comes in. All right, and if you do partial differential equations, you will see that there's also all these paraboloids, hyperboloids, these quadrics will come in, and these have got to do with maxima minima of functions of two variables if you want. And that's differential geometry there also. So there are many interesting things. So it's all once you do +2 and get in somewhere any decent place, within 2 or 3 years you will learn all this. But I'm saying that it's easy enough that you can learn it now. Okay, but of course it's all there's no pressure on you. You just learn it as a matter of enjoyment. And see, the nice thing is that how much of vectors, how much of calculus, integration, differentiation, okay, vector integration, vector differentiation, everything is put together. You put together some physical laws and then you get this equation, you derive this. So it's a complete synthesis of how to get the theory behind these equations, and then how to solve it. You write solutions. There is graphical software. You can plot it and see how it really looks, and then you can really see whether it matches with what you really see in real life. So you you take a rope, you fix it at one end and give it a kink, then this travels and then it comes back. Can you really simulate that? If you can really simulate that, you write the theory, write the equation, graph it, plot it and show it, then you have succeeded. Okay, but yeah, there are many. In fact, Wolfram is there, GeoGebra is there. There's also something called Simiode, which is especially for differential equations, mathematical modeling. Okay, so there are many, the hordes of software. Many of them are free. You can try that. It's very interesting. So that's okay. So I will stop. I don't want to stop, but I'll stop. Okay. Okay. You also don't want to stop. That's nice. So I'll catch you. I think now the lectures are all getting full. At some point, whenever I find a gap, okay. I mean, my course is over. My exam is next week. So there's somewhat I'm free. Okay. So I will see if there is a slot. I'll just jump and I'll try. I would like to give you at least one derivation, so you see everything come together. Okay. Yeah. So see you. Yeah. So please ask if you have any doubts. Please ask me. Otherwise, we will stop here. All right. So yeah. Yes. Any questions? No questions. Yes.
So when you how would the mean value point by integrating over the surface of the sphere? How did you integrate with just two iterations? An equation involving three variables.
No. What did I do? Very good question. Yes, it's a very nice question. So here, what you're asking is, I'm integrating on the surface of this. 11:30 ஆரம்பிக்கணுமா? சரி. So right. Okay. So as he suggests, there are time constraints. We discuss this over tea outside. But let me tell you very quick, 1 minute high speed answer. See, I'm saying integrate over the sphere. You understand his question? Yes, this is a 3 variable function. Yeah. Okay, and I should have corrected this. I didn't correct this. I should put ds because it's area integral. Yeah. Okay. Here's the interesting thing. How do you integrate? You have to parameterize. When you parameterize, you are parameterizing on the surface of the sphere. So what will happen is that x will become x of s comma t, or let me put it as u comma v. Everything will become 2 variables. Because your region is a sphere, surface of the sphere is a 2-dimensional object. So it is controlled only by 2 parameters. So what will happen is x will be x of u comma v, y will be y of u comma v, and z will be z of u comma v. And here what will happen is you will get some Jacobian times du dv. So this Jacobian will be change. You're basically what you're doing is you're changing variables to UV. No, when you do this change of variables in UV, this D originally I wrote ds. That's a small portion of area. When you scale it in terms of UV, it will become du dv. There will be a scaling factor. That scaling factor is this Jacobian. Okay. So what will happen is that this u will become now u of x of u comma v, y of u comma v. I'm sorry, I have used uv because there's already a u. I should have used something else. No, you understand. I should have used st or something like that. I should have used s and t. So this whole thing will be variable of s and t, and you'll get ds dt.
Yes, sir.
Clear? Good answer question. It's very important. Very important. Hi.
I would like to express my heartfelt gratitude to Professor Venkata on behalf of the class for the fascinating lecture about differential equations. The lecture filled with open discussions and new concepts about calculus made our session really very interesting. The laws of nature existing as differential equations and the connection of calculus right from the depths of nature were astounding. Thank you so much, sir, for giving us a glimpse of the big ocean of analytical functions and calculus.
Swayam Prabha. Digital India. Educated India.